In this video, I want to talk a bit about the ontology of spontaneous collapse theories. So we saw in previous videos that spontaneous collapses being built into the theory means that we do not have to separate the world into the quote-unquote quantum realm and the quote-unquote classical realm, the way we do with textbook quantum mechanics in order to explain away why there are no superpositions in macroscopic objects. So in the previous video, I talked about how when we have many entangled particles, such as in a macroscopic system, we have collapses occurring once every 30 nanoseconds or more. And so the objects would be in the superposition state for very tiny amounts of time that we wouldn't actually be able to notice. But recall, though, that the ontology problem is that the wave function for an n-particle system, which is what we were talking about in the previous video, is a 3 n-dimensional configuration space. So for n equals 1, this translates well into 3-dimensional space, but if we have many particles, if we have n greater than 1, there is no way to map 3 n-dimensional configuration space onto the 3-dimensional real space in which we actually live. And this means that the theory does not actually say anything about what the real physical world is made of. Or as Ghirardi puts it in the Stanford Encyclopedia of Philosophy, in its standard formulation interpretation, quantum mechanics is a theory which is excellent. In fact, it has an unprecedented success in the history of science in telling us everything about what we observe, but it meets with serious difficulties in telling us what there is. So there are two ways the GRW theory approaches ontology. There is the matter field ontology, or GRWm, and the matter flashes ontology of GRWf. So I will talk about each of these a little bit here in turn. So the first one we'll talk about is GRWm, which is actually the one that Ghirardi favors, but this is somewhat based on some of Schrodinger's early attempts to fix the ontology problem in quantum mechanics. So his early attempt at this was to posit that the wave function in configuration space could be used to define a mass density associated with each individual particle according to this right here. So this is our mass density. We're essentially taking the mass of particle I right here and multiplying it by the wave function throughout all of space. And so that's essentially smearing the mass out throughout space. And then the total mass density of space is just the summation of all of these mass densities for each particle. So this rho of x and t is a field of continuous matter density that would contain an image of the macroscopic world. However, with superpositions of simultaneously alive and dead cats, among other things, this matter field becomes exceedingly messy. So you would essentially have matter that is smeared between, say, an alive and a dead cat occupying the same space, and that can get very messy. So this led Schrodinger to ultimately give up on this interpretation of the wave function. Now, if these superposed states never last very long, so only nanoseconds at a time, then the matter density field becomes a lot clearer with less ambiguity. This way of thinking about GRW theory, as I said, is often called GRWm, where the m stands for the mass and mass density field. In this way of thinking about the ontology of GRW theory, a particle has its mass smeared out through space, but this smearing out is sometimes stochastically and spontaneously sharpened at a particular point. So I made this figure here to try to illustrate this. So we have our wave function right here, which is 2 sigma wide, and these collapses happen every so often given by our tau right here. And so what we're looking at is that when we are in the sort of wave function part of this, these are the times in which the matter is smeared out in a field. So the darker parts here in the middle are telling us there is higher density matter, and so we see that the higher density is localized right here. But then where I have these dots, this is times in which the matter localizes to a single point. And so we can have the matter localized to a single point, and then only from there will it start spreading out into its superposition, only to then in the future collapse back again into a point, and so that ensures that we end up with only localized and singular macroscopic objects. So there is a problem here that some people have pointed out, and this is the so-called problem of tails, which is that the Gaussian becomes extremely small but non-zero outside the peak of the Gaussian. So the way I have it up here, it looks like these kind of end as they go here, but it would actually be non-zero going off into infinity in all directions. And so this is sort of explained away in this paper here by Egg and Esfeld by saying that there is nothing indefinite about the position of objects according to GRWm. It is just that an extremely small part of each object's matter is spread out through all of space. But since the overwhelming part of the ordinary object's matter is confined to a reasonably small spatial region, we can perfectly well express this in our inevitably vague everyday language by saying that the object is in fact located in that region. So the region sort of here right in the middle of this. So they also say in this same paper that it is tempting to think of GRWm as similar to Everettian many worlds. So we saw up here that this can have the matter density here, but it can also be off somewhere else in space. And so we might think of this as almost a many worlds interpretation. So Egg and Esfeld say in the paper, a related problem that has received far less attention in the literature, but is actually more serious for GRWm, is the problem of structured tails. Consider a situation in which the pure Schrödinger evolution would lead to a superposition with equal weight of two macroscopically distinct states, say a live and a dead cat. The GRW dynamics ensures that the two weights do not stay equal, but that one of them, for example, the one pertaining to the dead cat, approaches unity while the other one becomes extremely small but not zero. In terms of matter density, we then have a high density dead cat and a low density live cat. The problem now is that the low density cat is just as cat-like in terms of shape, behavior, etc., as the high density cat. Thus, it is unclear on what grounds we could disregard it as unreal. But then it seems that GRWm is actually a many worlds theory, as this paper points out. And so this is quoting from this other paper within the paper that I am quoting. There is one high-density world and many, many low-density worlds, largely uninfluenced by one another, each with a right to be called macroscopic and physically real. One is, sure enough, of much higher density than the rest, but all are equally real, equally structurally stable, equally functional. What, then, is the significance of the density? Could we have any reason right now to feel assured that we are high density rather than low density objects? And then Egg and Esfeld continue. It is, however, not quite true that the low density worlds are structurally as stable as the high density world. Due to the shape of the Gaussian, in particular its tails, the low density worlds suffer distortion effects whenever the wave function collapses. And then they cite this paper, which I will actually talk about here. And so this is just kind of a figure that I made trying to illustrate what they're talking about here. So we start here in this world where it's smeared out between the alive and dead cat equally, but then this one, the alive cat, so the paper used dead cat, but I want to keep the cat alive here, is the one that ends up becoming localized in, I guess, what we could call alive-dead space here. And so we end up with the living cat, but we see that the dead cat here still has a very, very tiny but non-zero peak. And so we end up with this sort of low-density dead cat here. And so, as I said, this last reference given in this paper up here, which is the Wallace 2014 paper, points out that multiplication by the Gaussian not only substantially shrinks the wave function in the tails, but also shifts, or what Wallace calls kicks, the peaks of the wave function closer to the peak that is increased. And so this is quoting from this paper here, They say the effect of collapse on the tail peak is to displace it towards the collapse center. From the point of view of an observer in the tail of a Schrödinger cat state like, the effect of this particle is kicked by the collapse. Furthermore, since the tail's amplitude is very small, any subsequent collapses will almost certainly not prefer, that is, be centered on the tail. So all other particles in the tail whose counterparts in the main part of the wave function are spatially separated from them will also be kicked if they are subject to collapse. What he means by kick is this. So we have here in purple, this would be our two peaks, our sort of superposition of possible states here. But then when one of them is collapsed onto, so say this one over here at the left, this peak right here is actually kicked to the left over here. So the peak here after the collapse is actually shifted over somewhat. And so when we end up doing this multiplication by the Gaussian, we are not only shrinking the peak, but we are also kicking it in the direction towards where the main peak is. And the result of this, as Wallace discusses, is that life in the tails is not a good place to be. And I'm going to quote them at length here. So Wallace says, to see the practical effects of this, suppose that we prepare a Schrödinger's cat state, a macroscopic object of, say, 10 to the 27 atoms in a superposition of two locations a couple meters apart. Within 10 to the negative 14 seconds, assuming a GRW collapse frequency of 10 to the negative 16 per second, the first collapse will occur and the amplitude of, say, the second term in the superposition will be drastically reduced relative to the first term. The macroscopic object contains 10 to the 28 nucleons, 10 to the 28 electrons, and 10 to the 12 of these will undergo dynamical collapses per second. This will have a completely negligible effect on the first term in the superposition. The nucleons and electrons represented by the second tail term, however, will be kicked towards the locations of their counterparts in the first term. Set aside the kick to the electrons for now. The kick to the nucleons will kick each nucleon clean outside the nucleus. So saying right here that the kick will be far enough in space that it will actually move these particles outside of the nucleus. The nucleus will move a certain amount. These particles will move less than that, say, or more than that, and so they will actually be outside the nucleus. Due to the short range of the nuclear force, this will cause the nucleon to be ejected from the nucleus entirely. The structure of the nucleus is complicated and not that well understood quantitatively, and in case we lack a fully satisfactory version of dynamical collapse theory for nuclear physics. But in qualitative terms, this will lead to at least 1. Gamma radiation as the remnants of the nucleus settle down from their currently highly excited state into the ground state appropriate to the new number of protons and neutrons in the nucleus. 2. Possible beta and alpha radiation or electron capture, since the remnant nucleus is probably unstable. And 3. If the ejected particle is a neutron, then beta radiation as it decays. For instance, a collapse hit on a neutron in the nucleus of a carbon atom kicks the tail component of that nucleus into a highly excited state of carbon-11, which, assuming it is not so excited as to break up altogether, rapidly emits gamma radiation as it relaxes to the ground state, and then decays via electron capture to boron-11, emitting 2 mega-electron volts. The neutron decays in about 10 minutes into a proton-electron-neutrino pair and emits 1 mega-electron volt in doing so. So then skipping a little bit here, he goes on to say the decay energies quoted above, the 3 mega-electron volts, are fairly typical of the energies produced by dynamical collapse-triggered decay. As such, a kilogram of matter in the tail which is displaced by more than a meter or so from its high weight counterpart will emit energy at a rate of 10 to the negative 16 decays per second per nucleon times 10 to the 27 nucleons per kilogram times 1 mega-electron volt per decay, which is equals about 10 to the 11 mega-electron volts per second, or about 10 to the negative 8 watts. This should be taken as a lower limit, as it makes no allowances for gamma radiation when excited states de-excite. A large fraction of this energy will be in the form of a highly ionizing beta radiation caused by neutron decay. This level of radiation will be harmful to living creatures in the tails. Precise calculation seems inappropriate given the very rough nature of the estimates used so far. Note, however, that if a living being, say Schrodinger's unfortunate cat, were to be displaced by more than a meter or so from its high weight counterpart and were to absorb all of the ionizing radiation emitted by its own radioactive components, a reasonable order of magnitude approximation given the relatively high cross-section of beta radiation with matter, it would receive a radiation dose of 100 rem per year. This compares very unfavorably to the Environmental Protection Agency's recommended safe human dosage of 100 millirem per year. The EPA quotes 400 rem as the threshold fatal dose. And this is only the radiation exposure from the being's own body and does not take account of likely radiation from surrounding matter. And then he goes on to say the overwhelmingly high probability agents will either observe quantum statistics very close to the averages predicted by quantum mechanics or in due course die of radiation sickness. So the other ontology we have is GRWf. So the other way of thinking about the ontology of GRW is that each spontaneous localization at a particular time and location in 3D space produces a sort of matter point at that location in space-time. These matter points are often called flashes, and so this is known as GRWf, though Bell, who was the one who actually came up with this idea, didn't use the term flashes. He called them the local beables. So this paper here, Esfeld and Geisen, 2013, the way they put it is GRW quantum theory modifies the Schrodinger equation, or the Dirac equation, such that this law includes what is known as the collapse of the wave function. This law then is linked to the primitive ontology in the following manner in GRWf. Whenever there is a spontaneous localization of the wave function in configuration space, that development of the wave function in configuration space represents an event occurring in physical space, namely there being a flash centered around a space-time point. The flashes are all there is in space-time. That is to say, apart from when it spontaneously localizes, the temporal development of the wave function in configuration space does not represent the distribution of matter in physical space. It represents the objective probabilities for the occurrence of further flashes given an initial configuration of flashes. As in Bohmian mechanics, there hence are no superpositions of anything existing in physical space. However, by contrast to Bohmian mechanics, GRWf does not admit a continuous distribution of matter. There are only flashes being sparsely distributed in space-time, but no trajectories or world lines of anything. And so we can think about it like this. So again, we have this here where this is our wave function. We see it is collapsing, but now instead of having a matter density field, in these places here where it is not collapsed, these are times in which nothing exists in real space, only in configuration space, which means that our physical world is empty actually quite often. And so this paper here from 2007 says that note that if the number n of the degrees of freedom in the wave function is large, so essentially saying that a large number of particles, as in the case of a macroscopic object, the number of flashes is also large. So if lambda equals 10 to the negative 15 flashes per second and n equals 10 to the 23 particles, we obtain 10 to the 8 flashes per second. Therefore, for a reasonable choice of the parameters of the GRWf theory, a cubic centimeter of solid matter contains more than 10 to the 8 flashes per second. That is to say that large numbers of flashes can form macroscopic objects, such as tables and chairs. That is how we find an image of our world in GRWf. Note, however, that at almost every time space is in fact empty, containing no flashes and thus no matter. Thus, while the atomic theory of matter entails that space is not everywhere continuously filled with matter, so essentially talking about how in an atom most of it is made up of empty space, so they are rather largely void. GRWf entails that at most times space is entirely void. So not only is most of space void, but so is most of time. So these flashes only occur for really infinitesimal amounts of time. So even though they're happening, every few nanoseconds, that means that there are nanoseconds of time where nothing exists, but then there are only very tiny infinitesimal fraction of a second where things do exist. So according to this theory, the world is made of flashes, and the wave function serves as a tool to generate the law of evolution for the flashes. So essentially, it's saying that the wave function is telling us where these flashes are going to occur. And so we can look at both of these theories using the idea of a measurement and what they would both mean for a measurement. And so this comes from the Foundations of Quantum Mechanics textbook by Travis Norson that I'm using. So the left panel here is telling us about the matter density field, and so on the panel on the left, it shows the matter density field associated with all the particles composing the pointer of our measuring apparatus. For the familiar toy measurement example in which the energy of a particle in a box is measured and outcome E2 is indicated by the position of the pointer. Here, the pointer consists of a lump of non-zero mass density that begins near y equals 0 and then starts moving to the right at a certain well-defined rate just after the measurement interaction begins at t equals 0 right there. The slight bulge around t equals 0 is meant to suggest that as the individual terms in the wave function begin to separate, there is a brief period of time in which the matter density field includes several superimposed possibilities. But after a tiny fraction of a second, a spontaneous localization picks just one of the possibilities, the rest disappear, or as we saw above, they are in the tail and they end up just decaying into radioactivity. And the matter density field contains just one realized possibility. The right panel shows the same situation but for the flash ontology. The black dots represent the discrete space-time point flashes, and something like the overall motion of the pointer to the right at basically well-defined rate can indeed be understood as a galaxy of such events. He puts that in quotes because that's essentially what John Stuart Bell called it. It is interesting to contemplate, however, the fact that in the same way that a real galaxy is mostly empty space, most of the time the pointer is, according to GRWf, literally nothing. That is, for the overwhelming majority of horizontal slices you could draw through this diagram up here, so corresponding to particular moments, the slice would intersect precisely 0 of the flashes. The physical world, according to GRW, is curiously sparse and pointillistic at the micro scale, though it coarse grains to produce a sensible image of the familiar world at the macro scale. And so that is what the measurements would look like for both of these ontologies. But anyway, that was everything I wanted to talk about in this video. I hope you found that interesting, and I will see you in the next one.